Hello, welcome to the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And we're in a little mini series here that I'm calling Balanced Incomplete Block Design. And this is part 8 of 8, where we use the R software to illustrate what we've done in the previous 7 videos. And each section is labeled according to the video that we did previously. So part 1 is model development, and we'll look at a model and setting up the design matrix and etc. Now this example, I truly don't remember if it was from some internet site or an example from Montgomery's book, but this is what we're going to use. And so let me enter it into a variable called BIB, which stands for Balanced Incomplete Block. I make the catalyst and block factors. When I use crosstabs to calculate, this is it. Now this is not accurate because it puts zeros where there's no data, and really that should be missing. And if you notice here, each block contains 3 observations. The treatment 1, the catalyst, is repeated 3 times, or each level is repeated 3 times. B is the number of blocks, A is the number of treatment levels, K is the number of, the number in each block, which is 3. Now let's set up the design matrix. And this is XB, so it stands for the block. So if you look at the observations, for treatment 1, it was block 1, block 2, and block 4. And then treatment 2, it went block 2, block 3, block 4, and etc. So let's set up the treatment part of the design matrix, and there's 3 replications for treatment 1, treatment 2, treatment 3, treatment 4, and we also need a column of 1s. Now the design matrix looks like this. Now it's a column of 1s which is for the mu parameter, and I actually do the block first. Now a lot of times you'll do treatment first and block second, but the way we manipulate this design, we can't create orthogonal spaces, so I move the treatments to the end, and that's probably explained better in part 1 of this little mini series. But here, the next 4 columns are block, and these deal with the treatment, and we will put the observations in a vector called y. Now in part 2, we look at the column space of the design matrix. Now we need to enter the library mass, which allows us to grab the generalized inverse function, and actually allows us to grab what's called a fractions functions, which is pretty cool, and I'll show you that in a second. So here we create J, which is the perpendicular projection matrix onto the column space of 1s. That's this column here in the matrix, and then M is the perpendicular projection matrix onto the whole column space. So X transpose X, generalized inverse X, that's M. Now we create the identity matrix, so it's a diagonal matrix of BK by BK. The perpendicular projection matrix onto X tau, this column space. It's actually not quite that column space, so what we do is we add a well-chosen 0, and then we manipulate that design matrix into orthogonal spaces. And this MT, which stands for M tau, is the result of that, and watching part 2, of course, would be better. I have to create M beta before M tau, because we use M beta. M beta is the perpendicular projection matrix on the column space of X beta, and then M tau is what we said. And notice in part 2 we said M was actually the addition of these 2 column space, the perpendicular projection matrix onto these 2 orthogonal subspaces. And so there's an all equal function that we can use to see, yep, they are all equal. Let's look at the rank, or not the rank, the dimensions of X is 12 by 9. A and B are both 4 in this example. They don't have to be. The rank of X is 7. The rank of I minus M beta X tau is 3. So that's A minus 1 actually. Now, here's this fractions function I was telling you about. And so it creates these matrices and then it attempts to put fractions wherever it can. But here it's 0. And in part 2, we create, or we partition the design matrix into X beta and then this I minus M beta times X tau into orthogonal subspaces of the original design matrix. And here I was just showing you that they are orthogonal. We do get 0 back. Now the least squares estimate of beta, let's look at that. Now I run this library function on PRACMA, and in there they have a function called null space that I really like. And anyway, I use that to create 2 different generalized inverses. So I call it GI1, generalized inverse 1, and GI2. And basically I just add in a vector from the null space. So it actually adds sort of nothing to it. And I'm going to run all equal. And if you paid attention to what I just ran, the numbers are so not the same. And we can go all equal and show, look, they're, it didn't say true. There's a mean difference of 4.2, whatever. But these next 2 commands, I check to see if they're inverses, or it does create a generalized inverse of X transpose X. So here, this little piece on the end is X transpose X, and the piece over here is X transpose X, generalized inverse of X transpose X, X transpose X, and they should equal if it's a generalized inverse, and it is true. And then I run the same thing, but I use the second generalized inverse, which is not equal to the first generalized inverse, to see if it is also a generalized inverse, and it is. Okay, so to create the least squares estimates of beta, it doesn't matter what generalized inverse we use. It's still a least squares estimate. And so here, BLSE, that stands for beta, the least squares estimate for beta. And this is one estimate right here that you can see. And here's another estimate. And they are so not equal. But these are 100% generalized, least squares estimates for beta. Now, the cool part of this is this next command. We take X times that least squares estimate for beta. And we use 2 different least squares estimates for beta, but the same X. And that creates what's called a fitted model. And notice that it creates a unique fitted model. And to me, that's kind of mind-boggling, that it's no matter what least squares estimate we use, it creates a unique fitted value or fitted model. In part 4, we look at the sum of squares error and the F test. So let's look at that. Here I run the balanced incomplete block design. Time is equal to block plus catalyst. And then let's look at a summary here. So it creates the sum of squares, the degrees of freedom, mean square error, and this is what we're going to recreate. So notice that I have Y transpose M tau Y. That's actually the sum of squares for the catalyst, and it's actually adjusted for block, and you can see that it is. The rank is the rank of that matrix in the middle in the quadratic form, which is 3, which equals to the degrees of freedom for catalyst. Excuse me there. We can also, since it's idempotent, we can take the sum of the diagonal elements of that M tau, and it should also be 3, and it is. Now the sum of squared error is always Y transpose I minus M Y. for any design matrix. And so we get 3.25 as expected. The rank of that matrix, I minus m, is 5, and you see that it is the degrees of freedom. We could also take the sum, and it is, so here I take the sum of I minus m, but since m is m beta plus m tau, I also sum that to see if it is the same, and it is. Now the blocks is y m beta minus j y, and let's redo the summary here. So you can see it's 55, and the sum of squares block is 55. That's what we get there. The rank is 3, as it should be. Now the reduced model, so I call, I store the results in mod 3, so we take out the catalyst and we only have block. And we look at this summary, and so we have a block effect, which is 55, and residuals is 26. Now let's look at the ANOVA here. And let me rerun these summaries so we can have them on the screen. And then we're going to run the ANOVA, which looks at the reduction in the sum of squares when catalyst is added to the model versus not being in the model. And I want to point something out here. So here, the results of the ANOVA, we have 26, and we have 26, we have 3.25, 3.25. And if we look at that difference, we get 22, and then of course the F and the p-value associated with it. But let's look at this. We get 26, so this is the sum squared error for the reduced model, and it is 26. So here, I'd like to point out that in R, you have to be very, very, very careful. So in model 1, I switched the catalyst and the block in the model. And let's look at the difference between those. So mod 1, so this is the results when catalyst was first and block was second. And here block was first and catalyst was second. And so in the summary of mod 2, we have the block effect. And then since this is the type 1 sum of squares, this is the sum of squares for catalyst, but adjusted for block. And this is what we want. And so in this summary up here with a summary of mod 1, we have the unadjusted sum of squares for catalyst, and then for block, it's actually the sum of squares for block adjusted for catalyst. So you have to be very, very careful because this design is not orthogonal. The type 1, type 2, the ANOVA approach to regression are all different. So you have to be very, very careful. Now, in part 5, we introduce some notation. I called it the double index notation. And I want to illustrate that. Let's see if I can even put it on. Oh, it fits on the screen. Good. So this is the M beta. So this is the perpendicular projection matrix on the column space of beta. And then I put the double indexes here that correspond to, treatment 1, block 1, treatment 1, block 2, treatment 1, block 4. So there's no 3. And in there, we introduce this double notation. And actually for this M beta, we say that it's an indicator function. And I think we called it delta J prime. And that's equal to 1. And of course, it's divided by K. And I wanted to illustrate that. So look at this. This would be J, and J prime is the second index here. But when those are equal, the indicator fired, so we got a 1, and then we divide it by K. So the next time it equals is here, right? So we got a 1 right here, and the next time it equals a 1 is over here, so we got a 1. And that goes all the way down. So let's look at this one here. So 2, 2. So J is 2, and whenever J prime is 2, then that delta J prime was a 1, and we divide it by K. So notice there's a 2, and we get a 1. There's a 2, and the next occurrence is over here, and then there's no more. And so anyway, that's kind of what we were, it's not kind of, it's exactly what we were doing in part 5 when we introduced this notation, and we dropped several indicator functions, and so hopefully this helped ingrain what we were doing in part 5. Now the estimability and treatment contrast. So this to me, I just find so fascinating. So X right here is our design matrix. And I want to take rows 3 through 7, and then I'm going to add them and store it in L, right? So clearly L is a linear combination of the row space, right? It has to be, because that's the way we created it. So now we take that L, when we use it as a linear combination of the least squares estimates for beta. And notice that these two least squares estimates are so different. You know, one, yeah, anyway. But when we take this linear combination of them, we get the same value. And to me, that's just, you know, if you could see the little bubble above my head go, you know, I just love that. So let's try it again. So X, let's take rows 1, 2, 5, and 9. I just picked those at random. Add them, store it in L, and that's what we do here. And now let's look at that linear combination of the beta parameter. And no matter what least squares estimate we use, that linear combination of those is unique. And that's just crazy. So here I create a linear, an L, that's actually not part of the row space, just to illustrate. Now when we take this linear combination of the different least squares estimates for beta, we get different values. It's not unique. It's only unique when it's part of the row space. And so actually that becomes a critical component when you're designing an experiment too. You have to think about that. So here we develop some treatment contrast. So remember the beta parameter. It has a mu, a beta 1, beta 2, beta 3, beta 4. And then it has tau 1, tau 2, tau 3, tau 4. So we want a linear combination of those beta parameters, but we want to isolate those taus. And this is what L2 represents. And then L3 is another linear combination, you know, a treatment contrast. And L4 is also. Now these happen to be what's called orthogonal, which will play a part in part 7 of this little illustration. But so P2 is, now I trick it a little bit. So I want to find the P2, P3, and P4, which in my videos I called row 2, row 3, row 4, that satisfy that, and here they are. So here's P2, P3, P4, and what that does is that's the exact linear combination of the design matrix that we need to get back L2, L3, L4. And if we see that, so let's look. So look at this. It's row transpose, you know, times the design matrix X, and then this we got the first contrast back. So that's what I did. And the same thing for the next three. So this row, or in this program it's P3, we get the L, or the, you know, the linear contrast back that we wanted here. All right, so now this creates unique least squares estimates because these are part of the row space. And if we take L2 times beta tilde, the least squares estimate, these are the exact unique least squares estimates. Now, in theorem 1, we looked at that if we take this L2 but isolate just the C1, C2, C3, C4 on the end, that, and we called that L. Actually, these were lambda. This stands for lambda 2, lambda 3, and then the shorter version we just called L. L had to be, you know, row transpose I minus M beta times X tau. that was part of theorem 1, and then I'm just showing you that it actually is, so that we do get this L back up here. And if we do that for the other two, we get what we thought we'd get back. And so that may make more sense by watching part 6. Now in part 7, we deal with orthogonal contrast. And so here we really only want the C1, 2, 3, and 4. And we're going to put them in C2, C3, C4. And those are the contrasts, the treatment contrast, the orthogonal treatment contrast. And now I need to load this library called EM means. It's the estimated marginal means. And actually, I love this function here. So we use model 2. So that was y equals block plus catalyst. And we wanted to look at these 3 treatment contrasts. And that's what we got here. Now these are the estimated means. So this is, they try to make it so it's very SAS-like. So the least squares means, that's what this is up here. Now these are the contrast sum of squares. And let's look at that. So L2 times beta. And remember L2, there's lots of zeros in the front, and then it's the C1, C2. And we better get minus 4.5, and we do. L3 times that least squares beta, we get minus 3, which is the same as a C3. L4, we get minus 3.7, which is the same. Now, the sum of squares associated with each contrast is this quantity here on the right. I'm just going to load them in. So it's 4.5, 12, and 6.25. Now let's add those together and we get 22.7. But now let's look at the sum of squares for treatments adjusted for block. And notice it's 22.75. And that's what this is, 22.75. So these orthogonal treatment contrasts partition the sum of squares treatment. And that's kind of cool and pretty fascinating in itself. So you can go in and dig down and find where the biggest effect is in those treatments by using orthogonal treatment contrast. Okay, well, the video's running long and I'm going to cut it off here. Hopefully you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.